Hello, my name is Markus. The video at the start is an introduction into the topic of this episode: steady state versus transient GRAL mode. If we take a look to the graphical user interface, we see that the GRAL transient mode is activated using this checkbox in the GRAL settings tab of the main window. But what happens in the background if you check this box, and what are the differences between the steady state and the transient GRAL mode? Well, let's go to the steady state mode. The steady state mode is similar to the calculation of a Gaussian plume. That means we get steady state plumes. One gets a steady state plume in a Lagrangian particle model if all particles are released and dragged until they leave the domain area. There's a second criteria, that's if a particle is trapped, for example between two buildings. In such cases the particles are removed because otherwise you will get artificial peak concentrations in such areas. The plume is calculated for one meteorological situation until the particle has left the domain area. That means the meteorological situation is constant until the particle leaves the domain area. And this results in steady state concentration fields. The plume is calculated for a steady meteorological condition until the particle has left the domain area. In the transient mode are all particles released continuously, and they are dragged until the dispersion time expires, or they leave the domain area, because we can't drag particles outside the domain area. But they are also removed if the dispersion time expires. The position of each Lagrangian particle inside the domain area is stored if the dispersion time has been expired. And that's the important difference, because in the next meteorological situations there are new released particles from all sources, and the stored transient particles are released too. And with this method we get original plumes from the sources and transient plumes from previous weather situations. This results in the transient concentration field, and the plume is calculated for varying meteorological conditions. What are the pros for the steady state mode? The calculation is faster because there is no need to calculate each hour of a year. We can calculate classified situations. Let's say if you calculate an entire year, you have to calculate 8,760 hours in the transient mode, and maybe some 100 situations, classified situations, in the steady state mode. That results in less disk space. And another important point, the emission modulation is a post-processing procedure. We will talk about this a little bit later. What are the pros of the transient mode? In the transient mode we support time-dependent exit temperatures and exit velocities. That means you can change the exit temperature and exit velocity for each weather situation. The transient mode gives better predictions for large domain areas and frequently changing wind directions, and for short-term concentration values. A buff release is supported, and you will get smoother concentration maps. Here we see an example. That's a simple point source. We have a low wind situation with 0.75 meters per second, 10 meters above ground. We have a wind direction of 235 degrees, neutral conditions, means stability class 4, and a dispersion time of 1 hour. So we see the steady state mode, we get a plume. The squares here have an area of 1000 times 1000 square meters, and in the steady state mode we get a steady state plume for this situation. In the transient mode, with one situation, we get a plume like this. Why do they look different? Take a look to the wind speed, 0.75 meters per second, and the dispersion time, 3600 seconds. That results in a plume extension of 3000 meters, and that's what we get here after one meteorological situation. Now if we calculate 4 constant situations with this wind direction, wind speed and stability class, then we will get this plume in the transient mode. There's a low additional diffusion due to the calculation method, but it's very similar to the steady state plume. Here we see a valley in the Tyrol, and we have a wind measurement station here, and we get a typical wind system, a valley wind system. We have a mountain breeze in the morning and valley breeze in the afternoon. The wind direction changes at noon from the mountain breeze to the valley breeze, and at night from the valley breeze to the mountain breeze. We see that there is a very low frequency for winds from northwest and from southeast, and we have 3 branches from the eastern direction and 3 branches from the southern direction and a little branch from the northern direction. Now we take this wind situation and calculate an example and a steady state and a transient calculation for a point source, a huge domain area and flat terrain. The squares here have an area of 1000 times 1000 square meters, and this is the steady state calculation. We will get the maximum concentrations near the source, and at low concentrations, that's a distance of 2 kilometers, we see a fingered structure caused by the wind directions. We have 3 of wind fingers here from the wind from the northeast, and these are the 3 fingers here. We have the northern wind with this finger structure, and we have a fingered structure from the southwesterly winds. And now we take the transient calculation. It's smooth. We do not get that fingered structure because we do not calculate steady state plumes, but we are calculating the real weather situation of each hour. The positive thing is that the maximum concentrations are almost the same. There is no relevant difference here. But we see a difference at larger distances for this low concentration. We have almost no concentration in the steady state mode, but we will get a concentration in this area in the transient mode. And the question is, why do we get a concentration here? And that's quite simple. In the steady state mode, there is a low frequency for these wind directions, and so we will get almost no plumes in that directions, and no plumes means no concentrations. But in the transient mode, we have the transient plumes, and the wind direction changes at noon and at night from southwesterly to northeasterly winds, and this results in additional concentrations here, because existing blooms are transported back in the opposite direction. What's happening in GRAL itself? We have the GRAL calculation core, and in the steady state mode, the core needs a classified meteorological situation, it needs sources, it needs source groups. Then we will get result files, and we can apply an emission modulation to the result files in the graphical user interface, and so we will get resulted concentration maps. In the transient mode, the GRAL core needs classified or unclassified situations, sources and source groups. The GRAL core needs information about the modulation, the emission modulation for each source group. The GRAL core gets this information with the file emission modulation.txt. Then we get result files from the GRAL calculation core, and then we simply need to take them and add them to get the pollution maps. Here we see an example of a transient calculation recorded with the GRAL graphical user interface. We have a point source here in the middle of the screen, and at the first situation we have a wind from the northeastern direction, and we get this bloom for this situation. Now we switch to the second situation, and the wind direction changes from northeast to northwestern, and we get this bloom. This bloom stems from the source itself, and we get a second bloom here. This second bloom, we call it a transient bloom, originates from the first situation and from the first bloom, and is the transient part of the dispersion. Now we switch to the third situation. The wind changes now to a southwestern direction. We get the original bloom from the source, that's here, and we see the transient blooms from the first situation and the second situation. That means the transient blooms result from previous situations. And if we start with the measured wind, we see the blooms for several wind directions, wind speeds, and stability classes. And maybe we stop if we see almost steady state bloom. That's an almost steady state bloom because the wind direction and wind speed is almost constant, and we get an almost steady state bloom. Well, I hope you enjoyed this episode. Goodbye and have a good day.